So describing oscillation, here's a couple questions that might be nice to seek an answer to, diving into this. So why does periodic motion occur? And what are the requirements for oscillation, for periodic motion? So what's interesting is we've already seen a system which demonstrates periodic motion, springs and elastic materials. That probably came up in your first physics course. So let me throw a couple equations up there that you should already be familiar with and understand. So there's Hooke's law for springs, so F equals negative kx, and elastic potential energy. So we had kinetic energy and potential energy, and there was two types of potential energy. There was gravitational potential energy, and there was elastic potential energy. My hand is moving so I'll write U sub elastic. So that was 1/2 kx squared, right? So you should already kind of know how to use those. So Hooke's law for springs, that just describes that according to some spring constant k, that the restoring force here is going to be equal to the negative of the spring constant times the position that the spring is in. So if you displace a spring quite a bit, right, and we usually had some block attached to it, if the natural resting state of the spring was maybe here, like this, right, then you've displaced it some amount. So if this is x naught, where it's naturally resting, you've displaced it to some amount x. And so based on that displacement there, you would then plug that back in for x, and the spring has some spring constant that's dependent on the material that it's made out of. My k's are a little odd. And this negative indicates that it's moving back, in the force will be back in that direction, which is restoring the spring back to its rest state. So if you stretch it this way, the restoring force will be back in the other direction. So that's kind of a key component to oscillation, this restoring force concept. So we've already seen a restoring force, Hooke's law for springs. So not everything is new. All right. And so what we didn't talk about was what happens to the spring after it pushes that box, or after it moves that box, right? So usually we're talking about the elastic potential energy stored up in that spring. And so we'd have some elastic potential energy, 1/2 kx squared, and it would do some work on this box here, right? So you probably remember doing work energy theorem equations. So you had the kinetic energy initially plus the potential energy initially plus whatever outside work done is equal to the kinetic energy at the second point plus the potential energy at the second point. And so we're usually interested in quantifying how much potential energy there was at the beginning, at the end, right? And how much that all changed. But we were focused on this block, whatever the spring was doing work on. We weren't too focused on the spring itself. But what happens, and we know this because we live in the real world, what happens to the spring is it'll go back and forth, it vibrates. So it pulls back and it compresses a little bit. So let me draw some sequence of events just looking at the spring. So first, if we have some spring attached to some stationary surface, let's say this is its natural resting state. And you can imagine a block on it if that helps. And we'll just say there's no friction or air resistance or anything. We're just not considering that at all. So let's say this is at its natural rest state. Nothing has perturbed the system yet, so it's at x naught. All right. So next, let's take the same spring, and somebody's going to pull back on it. So now it's really stretched this way, right? And so now the block is further back. So if x naught was still right about here, it has now been displaced to x. So what this causes is a restoring force, like we were just talking about, right up here. A restoring force, and that's F is equal to negative kx, right? X being this guy right there. What also is happening, if we were to take this as a snapshot, right when we let go, it has no velocity. So I'll do this velocity in green. So velocity would equal 0. And right as we let go, the acceleration is present because there's a force, there's a mass, right? F equals ma. And so using F equals ma and the restoring force from Hooke's law that we know to identify, we can write down that the acceleration is negative kx over m, right? So there is an acceleration present. It's negative, right? So if this is in the positive x direction, the acceleration is to the left. All right, so now we've let go. Same system, but we've let go and it's traveled some amount back. Let's say it's passing x naught again. All right, so now the spring is back here at x naught, but it's in motion. It doesn't just come right back to its starting position unless there's some damping force, but that's not how normal springs work. So it flies right past this position. But if we were to take a snapshot right when it was at x naught, its original position, it has some velocity in this direction, and that's going to be maximum velocity right when it passes, because as soon as it crosses that point and heads more in that direction, now the acceleration will begin to be in that direction, pushing it back, and so it's going to begin slowing it down. So at this center point where it is crossing its original resting state, we have no restoring force on it because there's no displacement, right? If you just plug in 0 for that x, right, there's no force. And so therefore, since there's no force, there's no acceleration at this point either, right? So then let's keep going a further frame. So now the block, this spring, is more compressed than it started. There we go. And it's, let's say, right about here. So if x naught is still here, then this would maybe be like negative x, right? If it's not losing any energy to thermal or drag force or friction, and there's no damping at all, then it would go all the way back and compress to negative x, the exact opposite amount as x. So now what's going on with force and velocity and all that? So now the velocity is 0 because it's come all the way compressed. And for a moment, the velocity is 0 until it starts heading back in the right, the positive x direction. The force is now maximal in that direction, but this time it's not negative kx squared. Well, it is negative kx squared, but you plug in a negative x, so I'll write it like this, right? So that would be positive, in fact, kx. So you have this restoring force this way in the positive x direction, wanting to bring it back towards its resting position again. And then the acceleration is yet again, it's the negative kx, but you plug in the negative x. I'll do it this way again. So it's positive kx over m. So acceleration is in the positive direction as well, and it's as large as it ever will be because you have the most negative x, the largest displacement off to the left that you're plugging into that. And so then it comes back to the center again, and it's kind of a repeat situation of 3 here, except for it's traveling in the opposite direction. But again, the force would be 0, and the acceleration would be 0. And this would continue forever with no friction or thermal energy losses. The motion would continue forever. So let me do something really cool here that didn't get shown to me until the end of the equivalent of this course, and I wished it was shown to me in the beginning. So I'm going to take a new color here. So let's say we have time on this axis and displacement on this axis, right? So this is x, and this is time. So you can kind of see a curve start to emerge here, right? And it's going to continue, right? And if it were to keep going, it would just keep going in this oscillatory way, back and forth, back and forth. Does this look like a function that you're familiar with? Right? I'm sure it does. So if you rotate this, if I rotate it 90 degrees, let's say the displacement is this way. We'll call that x now, and this is t. Then what we have started right about in the center. So what we have is my best ability to draw a sine or a cosine function, right? So this is the cosine function. What this oscillation follows, it's not like the cosine function or the sine function. It is that function. Why are these two things related? Something that's moving back and forth linearly on a spring, a block being pulled back and forth. Why does that have anything to do with the curve of a cosine function? How can those two things possibly match up in any way, shape, or form? So consider an object moving around the unit circle. So let me get a unit circle here. Nice and big. Boom, unit circle. So if we have some object, some particle, and it's traveling around uniform circular motion, which you may have covered in your first physics course. So it's traveling with constant angular frequency, if you remember those terms, that vocabulary. If you were to shine a light on this big, huge light here, and you shine a light onto it, and let's give this particle a little bit more heft here. Nice big sized dot. As it traveled around in this circular path, the projection of this particle, so it's starting here, and in the next instance, maybe we'll look at where the particle is there, and the projection would put that here, and then in the next instance, the particle is here, which would put the shadow there, and then it travels back. We'll do in between, so here, and so then the shadow is here, right? So you can see what I'm doing here. The projection of a particle traveling in a circle is a particle traveling back and forth on a line. And so you get this linear oscillation back. You restore that linear oscillation that we are seeing with the block on a spring. So to me, when I saw that, that was kind of mind-blowing. That's why sine and cosine are used so often to describe even linear oscillations. they're incredibly useful. These trigonometric functions can really lend themselves towards even linear oscillations. So what we're going to move into talking to next is, oh, and by the way, don't let my drawings satisfy you. Google for GIFs that show you cosine function, projection of cosine function, or projection of unit circle oscillation, or something like that. And you'll come up with some nice animations that people have made to show this, and even some videos maybe of actual lights with actual things traveling in a circle. But it really connects those two concepts in your brain. But hopefully I made the point at least a little bit here. What we're moving into next is something called simple harmonic motion. And we'll define that as anytime the restoring force, so that restoring force that we had, this is, not all oscillations are simple and harmonic, but it's a really useful simple case scenario to start with. And it just means that when the restoring force is proportional, we'll do this, is proportional, that's what that means, to the displacement. So in Hooke's law, in the spring, Hooke's law for springs, we had F equals kx, right? So this proportionality constant k is the spring constant, and x is the displacement. So they are, in fact, directly proportional. It's not F equals kx squared or anything weird. It's F equals kx. And so this spring motion here is simple harmonic motion. And so there's a lot of really useful equations that can come out pretty quickly if you identify that something is simple harmonic motion instead of just general periodic motion of more complex nature. So before we move into that, I'll identify just some general terms, kind of in a vocabulary sense, of things that we'll talk about and use when we're describing periodic motion. So I'll go this color. So we'll talk a lot about amplitude, usually denoted A, and that's the maximum magnitude of the displacement. We'll sometimes use the word cycle, and that's just what it sounds like. You're probably familiar with that. Just one trip around the unit circle, or one trip through a linear oscillation. So I'll say one round trip through oscillation. So you start at a starting position, go through one full vibration, and you end up back where you started. We'll talk about period, which is usually denoted by the letter T for some reason. And that's the time it takes to complete one cycle. So maybe T is supposed to stand for time, but oh my gosh. Where did we go? Yeah, so time per cycle. And a useful thing is that the period is equal to the inverse of the frequency, 1 over f. And frequency denoted f usually, is the number of cycles per unit time, exact inverse of period. Cycles per time. And usually the units that are used are per second. So that's what a hertz is. So 1 hertz, abbreviated 1 hertz, Hz. That's 1 cycle per second, or 1 per second, right? One thing per second happening, one periodic event per second. And also, rather obviously, frequency is the inverse of period. All right, so then angular frequency, which I kind of threw that out there before, and we've definitely, it's hard to talk and write two different things. We've definitely seen that term before. That's omega. It's not quite a W. It's like a more curvy W. But there's a real nice relation that may be clicking in your brain here. We have this angular frequency around the unit circle. So considering the unit circle and our knowledge of angular motion, it's how fast the oscillatory motion completes a full journey around the circle, one cycle. And notice that it's also consistent with our concept of omega as angular velocity. So angular velocity, remember, we were saying omega is d theta dt, right? So it's an angular version of velocity, and theta is an angle that kind of takes the place of linear displacement. So its angular displacement is theta, so the derivative of that with respect to time would be the angular velocity. And so it's all consistent. It's not two things that have been used, or one thing that's being used to describe two different concepts. It's the same concept. So angular frequency to describe one cycle of periodic motion is the same as talking about angular frequency as some amount of radians per second, or angle per second. And some useful equations for angular frequency is omega is equal to 2 pi frequency, because 2 pi is one way all the way around, and the frequency is cycles per time. So it just changes frequency into an angular version of it. So angular frequency kind of makes sense. Or, since the inverse of frequency is period, we can say that angular frequency is equal to 2 pi over t. All right, so next we'll talk about simple harmonic motion.